four coordinate is defined as an x mu, which is equal to x0, x1, x2 and x3. Okay, so this is by definition c times t, x, y, z. X, y, z is the spatial coordinates and c times t is the time coordinate. For momentum, can be written as E mu, which is equal to P0, P1, P2, P3, which is equal to energy divided by C. This is called time-like components, and these are called space components. Okay, so E by C, the x component, y component, and z component of the moment. So energy momentum is combined, and space-time is combined. Okay, you can write many four vectors. For example, for current density, you can write it as J mu, which is equal to J0, J1, J2, J3, which by definition is C times rho. The time-like component of current density gives you the charge density, and usual Jx, Jy, Jz. We can talk about four vector potential. A mu is equal to A0, A1, A2, A3, which is equal to phi by C, Ax, Ay, Az, where phi is the scalar potential, Ax, Ay, Az are the components of the vector potential. Now, for gradient operation, this I will write it as del mu, because as we said, gradient is a one form. It transforms like a one form. So del mu is equal to del 0. Please note that here I am writing subscripts: del 1, del 2, del 3, which by definition is 1 over C times dou by dou t, dou by dou x, dou by dou y, dou by dou z. The metric tensor for this four-dimensional flat space-time is given by G is equal to minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. What does this mean? That means if I have, so if I want to have dou mu, that is contravariant derivative, then I will get that by writing G mu nu dou nu. By multiplying dou nu with G mu nu, I will get dou mu, which is essentially minus 1 by c into dou by dou t, dou by dou x, dou by dou y, and dou by dou z. And any quantity which is written in the form of, for example, if you take supposing you have dx mu, which is equal to c times dt, dx, dy, dz, and corresponding dx mu you will get with g mu nu times dx mu, which is given by minus c times dt, dx, dy, dz. Remember, this is also same as its inverse. So I don't have a different matrix if I put it these indices as subscript or superscript, the same matrix. Now if I ask what happens to this quantity, that is dx mu, so if I ask what happens to this quantity, this will be minus c times dt the whole square plus dx square plus dy square plus dz square. This quantity is invariant under Lorentz transformations. This quantity is invariant under Lorentz transformations. In other words, if you have some equation which can be written in this form, which is form invariant under Lorentz transformation, okay, so this is actually invariant because this quantity will not change. Suppose if you say that you have dx prime of mu into dx prime of d mu is same as dx of mu and dx. There won't be any change. Their x prime are the coordinates which you get from Lorentz transform.